Now we're going to look at actually building the VaR models, the three different VaR models, normal, historical and Monte Carlo. Well, what data do we need? Typically, the probability distribution for the portfolio returns, or P&L, over the next H day is based on data for the recent history of the portfolio returns, or P&L, assuming that these are indicative of future returns, because the VaR is a forecast over the next H days. How much could we lose in future, not looking back? Banking regulation recommends that banks use about 3 to 5 years of daily data and a minimum of 1 year of daily data. The amount of data you need actually depends on the model. Historical VaR models need lots and lots of data. It can be difficult if you've got a portfolio with some bonds that didn't exist 5 years ago, and or you've got shares that have only just come on the market. There may be quite a lot of missing data for the historical VaR model. And as I said, if you've got a very small alpha, not just 1%, but like 0.1%, or even at 1%, you do need a lot of data to get some accuracy in the tails there. The other models are parametric, and you can estimate the parameters using just a bit of data. You can even make the parameters up, assume what their values are. All right, let's start off with the normal VaR. And the assumption on the portfolio H-day returns is that they are IID and they are normally distributed. And then if we have the mean mu h and sigma h squared, then our VaR is going to be phi to the minus 1 of 1 minus alpha times sigma h, the H-day standard deviation of returns, minus the H-day mean of returns. But when VaR is small, we very often assume that mu h is 0. And so really the VaR is just driven by the standard deviation of H-day returns. And it's just scaled by this number phi to the minus 1 of 1 minus alpha, which we know it could be, for example, 2.326 for a 1% VaR, or for a 2.5% VaR, it would be 1.96. For example, if we're looking at daily returns with mean 0 and variance or standard deviation 0.8, then the daily VaR 1 at 5% will be phi to the minus 1 of 0.95 times 0.8. That's the 5% VaR, which we use 1.645 for the 5% VaR. This is for the 2.5% VaR. This is for the 1% VaR. And so it's 0.8 scaled by 1.645, which is 1.316%. And because it's returns, we've got VaR as a percent of the current portfolio value. Now, recall that the standard normal transformation, this is how we prove this formula here, because I've just taken it out of the hat. I haven't proved it, so let me prove it now. Remember the standard normal transformation? If x has a normal distribution with mean mu and standard deviation sigma, then x minus mu over sigma has a standard normal distribution. So we've got our H-day portfolio returns. That's the random variable xh, right? And that's got a mean mu h, which is usually assumed to be 0 unless h is very large, and standard deviation sigma h. And we want to find the quantile xh alpha. How do we find xh alpha? If we can find xh alpha, then we just multiply it by minus 1 and we've got the VaR. But how do we find xh alpha? So it's the alpha quantile of the H-day returns. In other words, putting it mathematically, xh alpha is that number here, some probably negative number, such that the probability that the return is even more negative than this is just alpha, where alpha is usually just 1% or 5% or something like that. Okay, so let's use this standard normal transformation here. So I've got an inequality here, but it acts just like an equation. What you do to one side, like a set of scales, you've got to do it to the other side so that it still balances. So if I take off something from xh, I have to take off the same thing from little x, h alpha. So if I want to take away mu h, that is the standard deviation, I'm going to do x, capital XH, minus mu h over sigma h. So I get to do it to that side. I get z, because that's the, applying the standard normal transformation to that side gives me z. Applying the standard normal transformation to this side gives me this number here. Okay. So I know that the probability that z is less than this number here is alpha. Z is a standard normal. But by definition of the standard normal quantile, its probability that z is less than phi to the minus 1 alpha is alpha. So this number here must be phi to the minus 1 alpha. Now, turning this around, we can multiply mu h up there. And I want to find minus xh alpha. So xh alpha is going to be phi to the minus 1 alpha times mu h plus, sorry, sigma h, phi to the minus 1 alpha times sigma h plus mu h. Now, multiplying it by minus 1, that gives minus the quantile is minus phi to the minus alpha times sigma h minus mu h. And now I've got it, because this is the VaR. Minus xh alpha is the VaR. And so we get this normal formula, remembering that minus the inverse distribution of alpha is plus the inverse distribution of 1 minus alpha for the standard normal distribution, because it's symmetric, same for any symmetric distribution. We get the normal VaR formula. Remember, if we base sigma h and mu h on returns, then we still need to multiply by the current portfolio value. Here's an example. If we get the percentage VaR is 8% and the portfolio value is 20 million, then the dollar VaR is 8% times 20 million, which is $160,000. But remember, we can't always use returns. Sometimes we have to use P&L. We cannot calculate mu h and sigma h on returns. Instead, we have to calculate mu h in dollars and sigma h in dollars as a mean and standard deviation of the P&L distribution, using some historical data on the P&L, and then using the sample mean and the sample standard deviation of those data. So here's some numerical example for the normal VaR model. Given some data, calculate the 1% daily VaR for a portfolio that has value 1 million, is expected to return the discount rate with volatility 20%. Okay, so if it's expected to return the discount rate, your return is the risk-free rate, and then you discount it using the risk-free rate, the discounted return is 0. So the mean is 0 for our calculation here. The volatility is 20%. Assume the discounted returns are normally IID distributed and that there are 250 trading days per annum. Now, at the end of topic 3, we looked at the square root. So in the statistics section of topic 3, I can't remember, somewhere in topic 3, we definitely covered the scaling using the square root of time rule. And if we have a sigma 250, which is 20%, then sigma 1 is 20% divided by the square root of 250. I'll go over this again when later in the topic. If you find this a bit confusing, it'll probably become clear later on in a later video. So anyway, that gives us our standard deviation of returns, which we then multiply by the minus phi to the minus 1 of 0.01, or alternatively phi to the minus 1 of 0.99. You can put either there, and that gives us the critical value 2.326 that we use here, and it gives us VaR is 2.9426%. Multiplying that by 1 million, notice it's useful to keep a lot of decimal places in here in this calculation. I had 5 decimal places for the critical value, and I carried 6 decimal places here so that we get a dollar accuracy for the 1-day VaR. So don't round too much in your returns calculation. When you multiply by a large number like 1 million or 10 million, it really matters. And here's another example. What's the 10% VaR over a 1-year horizon of a $2 million invested in a fund, where you've got annual returns in excess of the discount rate are assumed to be normally distributed with mean 5% and volatility 12%. So this example, we do need the mean adjustment, because in excess of the discount rate, we still have a mean of 5%. So we take off 5% in the calculation. There's no need to scale because I've got a volatility of 12% and I want an annual VaR. I don't want a 1-day VaR as I did previously here. I wanted a 1-day VaR, which is why I had to divide the volatility by the square root of 250. But I don't need to do that because it's a 1-year VaR here. Keeping lots of decimal places in the calculation and then multiplying it by 2 million to get the VaR figure in dollars. What about other VaR models? Well, as I said, normal VaR assumes a portfolio as a linear function of its assets or risk factors. But the price of an option is definitely a non-linear function of the underlying asset price, so you can't use normal VaR for options portfolios. Another problem with normal VaR, which is the biggest problem really, is it assumes the asset or risk factor returns are normally distributed, and that's very unrealistic. Most financial returns are very, very what we call leptokurtic. They are not normally distributed. So historical VaR is a lot better in that case if you have the data. If not, you could use Monte Carlo VaR with a leptokurtic distribution assumption. For example, you might use a normal mixture distribution or a T distribution or something like that. So for historical VaR, there's 2 ways to get the historical data that we need. Either we assume there's no rebalancing and you keep the holdings constant, or we rebalance to constant weights. And since we're only looking at portfolio VaR at that level, we're not drilling back into the asset levels, we can make that choice as we want. However, if we want to drill down to how much risk is due to Tesla's stock, we need to use the constant weights assumption, because we'll be looking at the portfolio return, which is a linear combination of the weighted sum of the asset returns. Again, it's the ordinary returns, not the log returns we use here. And that linear function will then be put into a high-dimensional VaR calculation where we use the whole covariance matrix and the calculation W prime VW. I'll talk about that in much more detail in topic 6 when we get on to looking at VaR for equity portfolios. So at this level, though, we're just looking at a one-time series for the profit, the returns or the P&L on a portfolio, and we can make either assumption, either no rebalancing, keeping the shares constant, or we don't want to use this method because it's not very algebraically tractable, but we could use it if we're not going to go any further than looking at an historical VaR. And similar definitions apply in other contexts. So we could, instead of assuming that the portfolio weights are constant, we could assume that the sensitivities, because they take the place of weights when we look at a portfolio as a linear function of risk factors rather than a linear function of the asset returns, linear function of risk factor returns as opposed to asset returns. What about calculating VaR using historical simulation? Well, the alpha percent H-day historical VaR is just minus the alpha quantile of an empirical H-day discounted returns. Only the recent data reflect the current market conditions, but to capture the tails, we need a lot of data. So that's not very intuitive, really, because it's very difficult to collect sufficient samples, particularly if we want to look at 10-day VaR. We might be tempted to look at overlapping 10-day VaR, but that's wrong, because one big return will get hugely augmented. So you have to take non-overlapping returns, and you can't do that for 10 days unless you have 50 years of data. You wouldn't have enough data in the tails of the distribution. So typically, when we're calculating VaR, we have to do it on daily returns, and then we scale it using the square root of time rule, or we could use other rules, but we'll be looking at that in more detail in part 6 of this topic, scaling VaR. So we can't use overlapping data. One spike would come up 10 times, and then we'd get 10 massive points in the lower tail, for example, the upper tail, if it's a positive spike in returns. Monte Carlo VaR, again, we use alpha percent H-day, which is minus the alpha quantile of a simulated distribution, now not an empirical distribution. And we can use any parametric we want. It's very flexible, so we can model quite complex portfolios using Monte Carlo VaR. And the returns are simulated directly, or we could use it at the risk factor mapping, and we're going to describe it in detail, in particular in topic 7, when we look at options portfolios. Monte Carlo VaR is often more reliable than historical VaR when you've got a large H and a low alpha. Historical VaR is really not good because for a large H, you're compelled to, and particularly when the alpha is low, you need lots and lots of data, and you still have to have just daily data, and you're going to use the square root of time rule when H is a year. That's going to be completely impractical, so you need to be very careful how you scale it in that case. Monte Carlo, you estimate the parameters of your chosen distribution based on a smaller sample of 10-day returns. You know, you could have like 3 years of 10-day returns. So how many 10-day returns are there in a year? There are 25 per year. So, well, if you had 4 years, 8 years, you would get, well, even a sample of 100 is probably enough to get standard deviations or any, whatever your, I mean, different distributions have different parameters. It's not always just the mean and the standard deviation. That's just for the normal distribution or the t-distribution. Other distributions might have different types of parameters. Some distributions have 4 parameters, like the hyperbolic distribution. So you might have to estimate a lot of parameters, but the point is that you don't necessarily need a lot of data to estimate those parameters. And then you can simulate thousands and thousands and thousands of returns to get lots of accuracy in the tails. So how does Monte Carlo sampling work? The simulation from a random variable, well, suppose we've got a distribution fx, and we've estimated the parameters of this distribution fx, so we've got a distribution function here. Then for simulation, we just draw a random number u from the standard uniform, and the way to do that in Excel is equals rand, empty brackets. If you put something in the brackets, if you put a column of data in the brackets when you do equals rands, it will randomly draw from that column of data. But if you leave the brackets empty, it'll just give you a draw from a standard uniform distribution. And the standard uniform distribution has a density function which is a flat line over 0, 1. In other words, every number is equally likely between 0 and 1. And so you randomly draw, and the reason it's called Monte Carlo is this step here, the random drawing, like the Monte Carlo wheel. Each number is supposed to be equally likely, unless the casino has, put a bit of a tilt on the number 0 to make it less likely or whatever. Not all Monte Carlo wheels are equally likely, but that's where the term Monte Carlo comes from, the fact that these random numbers here are all equally likely. So you draw a number u, and then you use f to the minus 1u, and there are lots of commands in Excel. If you're doing it from the normal, which we shall do, you use norm_inv or norms_inv if it's standard normal. And you've got log normal, chi-squared, f, gamma, loads and loads of different types of simulation commands, depending on the distribution that you choose.